Let's look at the first two problems from this Taylor series FRQ worksheet number 1. This is AP review here. So number 1, it says find the first 5 terms in the Taylor series about x equals 0 for our function 1 over 1 minus 2x. And one way that we can do this is we can always build our polynomial from the formula for Taylor series, for Taylor polynomial, which is the nth derivative evaluated at c over n factorial times x minus c to the nth degree. So what we can do is we can find each of the derivatives up to the fourth derivative. So starting here, what we can do is we can bring the 1 minus 2x up to the numerator, and we can go through quotient rule to go through find f prime. So bring down the -1, keep the parentheses, subtract 1 from the exponent. -1 minus 1 is -2 times the inside function's derivative. And then we go through the process again to find the second derivative. So the second derivative would be bring down the -2 and then multiply by or subtract 1 from the exponent and multiply by the inside function's derivative. So we get -2 quantity squared, and then we go through the steps again. So bring down the -3, multiply inside function's derivative, bring down the -4, subtract 1 from the exponent, and multiply by the inside function's derivative. So we see this pattern building up. And then if we want to evaluate each of the terms at each of the derivatives, we're going to plug 0 in. So plug 0 into each of the functions and each of the derivatives. F of 0 is 1, f prime of 0 is 2, and then we get 8, and then 3 factorial 2 cubed, and then 4 factorial 2 to the 4th. Okay. And then we build our Taylor polynomial here. So the first two terms is always going to be a linear, the slope of the tangent line here. So f of 0 plus the slope times x minus 0. And then we start our pattern. F prime is double prime of 0 over 2 factorial. F third derivative evaluated at 0 over 3 factorial. Fourth derivative evaluated at 0 over 4 factorial. And then we plug each of those values into these respective values. And then we get 1 plus 2 times x minus 0, 2 squared x squared, 2 cubed x cubed to the 4th x to the 4th. And we can also create our general rule by looking at the pattern, right? So we can either start at 0 or start at 1, depending on which way is going to produce this, the simpler of the rule here. So we see that the pattern is that each of the variable and the exponents, and the coefficients exponents have the same degree. So this is 2x squared, 2x quantity cubed, 2x quantity to the 4th. So we can create this rule here. Okay. Another way that we can find the first 5 terms in the Taylor series is if we see this as a geometric series, which is a sub 1 over 1 minus r, then essentially we can just treat this like the first term, and then each subsequent term we can multiply by our ratio. So 1, there's the first term. Second term is 1 times -2x, which is -2x. Oh, sorry, ratio is just a 2x. So 1 times 2x is just 2x. And then the next term is going to be 2x times 2x again, so 4x squared, and then so on and so forth. So there's 2 ways that we can go about getting to our polynomial. We can either build it from scratch, or if it matches one of the geometric rules, if it matches a geometric series, then we can use that step as well. All right, part B, find the interval of convergence. So interval convergence based off of part A, we have a rule of sequence for part A. So to find interval convergence, we can just go through ratio test. So the ratio test is we know that the series is convergent wherever the limit as n approaches infinity for a sub n plus 1 divided by a sub n if the absolute value of that is less than 0. So let's do a sub n plus 1 first. A sub n plus 1 is 2x quantity raised to the n plus 1 divided by a sub n divided by 2x to the nth. So really this is 2x quantity to the nth times 2x to the first power. The 2x to the nth will cancel out, leaving us with just absolute value of 2x. The absolute value of 2x is less than 1, wherever the absolute value is less than 1/2 if I divide both sides by 2, which means that x is between negative 1/2 and 1/2. Now, this only gives us a potential radius or interval convergence. We always have to make sure we test the endpoints with the rule of sequence because the endpoints may or may not diverge or converge. So we can plug 1/2 into the rule of sequence. 1/2 times 2 is just going to be 1 to the n. 1 to the n, if we think about what this series does, is 1 plus 1 plus 1 plus 1. It's going to go all the way to infinity, so we know the series will diverge. If I plug negative 1/2 in for x, we get 2 times negative 1/2, which is negative 1 to the n. And if we think about this rule of sequence, we get negative 1, we get negative 1 to the 0, so 1, and then minus 1, then plus 1, then minus 1. So the series, the partial sum, will keep jumping between 0 and 1 and negative 1, so it will never converge on a nice value. So we know that both these endpoints will diverge. So interval convergence is negative 1/2. X is between negative 1/2 and 1/2. Okay, part C. Use partial fraction and the result from part A to find the first 5 terms in the Taylor series about x equals 0. For here's the function 1 over 1 minus 2x times 1 minus x. We're going to use partial fractions. We're going to split these parentheses into 2 separate fractions. So split up into a over 1 minus 2x plus b over 1 minus x. And then our goal is to find out what to put in place of these numerators. Okay, so let me walk through the steps here. We can go through a cover-up method, which essentially we look at the 2 denominators and we find the critical points that will cause it to be 0. So if I set 1 minus 2x equal to 0, x equals to negative 1/2, or x equals positive 1/2. If I set 1 minus x equal to 0, I get x equals 1. So the way the cover-up method works is if I'm trying to find the value that will go in the numerator above 1 minus 2x, what I'm going to do is I'm going to cover up the 1 minus 2x and then plug in the critical point into the remaining x's for the remaining expression. So if I plug 1/2 in for the x, 1 minus 1/2 is 1/2. 1 over 1/2 is 2, so 2 will be the a value, the first value that gets plugged in to the numerator. Okay? If I want to find out what goes in for the numerator above 1 minus x, I can cover up 1 minus x and then take the critical point, which is 1, plug it into all the x's of the remaining expression. So 1 minus 2 times 1, so it is negative 1, so 1 over negative 1 is negative 1. So now we have the partial, well, we have the equation split up into 2 separate fractions, and should be easier for us now to identify the series that goes along with these rational expressions here. So we see that both these terms match geometric series because we have a sub 1, we have 1 minus r, so here's our ratio for the first series. So what I can do is I could factor out the 2 and then just treat this like a 1. So 1's the first term, and then plus, and 2x plus 4x squared plus 8x cubed. So every term I'm multiplying by the ratio, which is 2x. Okay. Same thing here. Negative 1, I'm going to factor that out here. And then I'm left with 1 over 1 minus x. So really, first term is 1, and then every subsequent term I'm multiplying by x. So 1 plus x squared plus x cubed plus x to the 4th. So all this, there's a minus in front of that coefficient. And then if I distribute and combine like terms, all we want is for the first 5 terms of the Taylor series. So we just have to combine these terms here and combine like terms and get the first 5 terms. Okay, so distribute this through, we get 2 plus 4x plus 8x squared plus 16x cubed, 32x to the 4th. minus, and then distribute the negative through all the way. Now let's combine like terms. So 2 minus 1 is going to be 1. 4x minus 1x is 3x. 8x squared minus x squared is 7x squared. 16x cubed minus x cubed is 15x cubed. 32x to the fourth minus x to the fourth is 31x to the fourth. 1, 2, 3, 4, 5. Here we have 5 terms. So this is the first 5 terms of this Taylor polynomial. Okay, let's look at number 2, second page here. Determine all the values of x for which the series will converge. We can also need to justify our answer. So let's see if we want to find where the series converge, we can just jump directly into ratio test. So ratio test is limit as n approaches infinity for a sub n plus 1 over a sub n. So a sub n plus 1 I can replace, or in this case a sub k plus 1, I can replace every k that I see with k plus 1, okay, divided by a sub k. And dividing by a sub k is the same thing as multiplying by the reciprocal. So the reciprocal of a sub n, a sub k, I can just flip the numerator and denominator here. So let's see if we can clean this up here. So natural log of k plus 2, natural log of k plus 3, we can put that off to the side here. 2 to the k plus 1 will cancel out with 2 to the k, leaving us with just 2 to the first power. X to the k plus 1 will cancel out x to the k, leaving us with just x. So we're left with 2x, natural log of k plus 2 or natural log of k plus 3. And if we try to evaluate the limit of this expression, we know this will just cancel out, leaving us with just 1. Cleans out nicely. So we're left with just absolute value of 2x is less than 1. Divide both sides by 2. Absolute value of x is less than 1/2. So that means x is between negative 1/2 and 1/2. So we also have to test the endpoints. So let's plug negative 1/2 into the rule of sequence. So I'm going to replace every x I see here with with positive 1/2. So when I do that, I get 2 to the k times 1/2 to the k combines to be just 1 to the k. Now 1 to the k over natural log of k plus 2, if we think about this, we may not know whether this converges or diverges, but if we try to compare it with a known series that's similar, let's think about 1 over k plus 2, for instance. We know 1 over k plus 2 is just going to be a variation of the harmonic series, which we know will diverge, right? We know that natural log k plus 2 is less than k plus 2, but because this is in the denominator, that's going to turn everything opposites in the sense that this is actually going to produce a larger value than 1 over k plus 2. And because we know 1 over k plus 2 will diverge, anything greater than a diverging series must also diverge as well. So we can say that since 1 over k plus 2 diverges, by direct comparison test, we know that 1 over natural log k plus 2 also diverges. So therefore 1/2 is not going to be part of a value that we can confirm will converge. We know 1/2 must diverge. Okay, if I plug negative 1/2 into the same rule of sequence here, negative 1/2 plugs in for x. 2 times negative 1/2 is negative 1 to the k over natural log k plus 2. Now this is going to be an alternating series because every other term is going to change signs, or each term is going to change signs. Each subsequent terms will change signs. So basically, for alternating series tests, for it to converge, all we need is the absolute value of this rule of sequence for the limit of the rule of sequence to go to 0. So we know that 1 over natural log k plus 2 as k approaches infinity will go to 0. So that's enough to show that the series will converge. So that means we have to include negative 1/2 as a value that will converge. So therefore interval convergence is between negative 1/2 and 1/2, with negative 1/2 included, but 1/2 not included.